Well, hello, team. We're back again. So we just bludgeoned you with heat, right? We introduced thermodynamics or thermochemistry specifically, got some of the terminology, signs, was energy going in, energy going out. Kind of introduced the first law of thermodynamics and how we're going to think about it. Now we did the big picture first, and now we're looking at the details. So we looked at heat in the last video, and now we're going to do work. That's the only two ways we can change the internal energy, right? Loss of energy through heat flow, right, due to temperature changes, or loss or gain of energy, depending on who's doing the work on who, um, from work from the system to the surroundings or surroundings to the system. Piece of cake, right? Our focus will not really be on the work as much. It's going to be, like I said, it'll probably at least 90% heat. What's your chair, Benji? Gotta service the kitty cat. So this video will cover work. It's going to be a pretty quick one. Not going to go into gory detail. Used a lot more in physics, but we're going to look at it from a chemical perspective. So we'll introduce the physics perspective first, and then we'll look at it from a chemistry perspective, and then we can combine work and heat and calculate delta U in those situations. And then we're going to go back to heat again and look at all the different ways we can measure heat flow in labs, right, through what's called calorimetry. And we're going to spend the rest of our time on heat pretty much. All right. So my physics friends, if you remember, work is force times distance, right? Probably in physics, you probably had some block or something like that, and there I am there pushing on it, or whoever that is. I got to push this, and and you're applying a force over some distance, and now you're sweating, and I haven't been in the gym forever now, so just doing anything makes me just gas. It's like, I want my gyms to open again. So if you know the distance and you know the forces involved, you can calculate that. So this might be a little more challenging. Maybe if we did it up and down, right, lift something, right? So if I lift it from the bottom of the board to the top of the board, I know the distance. And the force in this case would be the mass of this object times the gravitational acceleration constant g. So I can actually calculate that. So all this stuff we can do with physics. But chemistry, we're not going to be pushing cement blocks around, like that. So we tend not to sweat in chemistry. So kudos to my physics friends out there. Go Arnold. So in chemistry, we tend to look at it as far as a gas expansion or a gas compression, because we use gases, right? Hey, solids, liquids, and gases. Hey. And if you're fancy, plasmas. And so let's say, example, we had a chemical reaction where we started with a set number of moles of gas, and that increased the number of moles of gas. Well, that's going to expand, right? And it's going to push against, if it's in a container, it's going to push against the walls of those container. Maybe we have a piston that moves up and down. If it's not, that container could explode, right? And if it's open, right, it's going to expand against the surrounding atmosphere, pushing back against it. So there's work, right? So if you're expanding a gas, it's working against the external pressure of the atmosphere, pushing against it. Or if the pressure is pushing against it, maybe we compress the moles of gas, or the external pressure pushes against it and collapses the gas down. There's going to be a compression of the gas, and that involves work of these surroundings on the system. So we'll look at the signs and the same thing, but we're going to look at this gas compression and expansion work. It's called PV work in the world of chemistry. We're not going to be pushing blocks around. Hey, let's look at some PV work. I couldn't get this all on one board. I really tried, but we're going to have to do some calculations. Well, not calculations, derivations on the next board. We're really after an equation like we did for heat, right? We had the Q equals ms delta T for temperature changes, Q equals N times delta H for phase changes. So we can actually calculate heat changes. For work, we want to get the same thing. So this is kind of the first part of two in deriving an equation. Only one, yay, for calculating work from gas compression or gas expansion. So let's look at gas expansion and compare it to gas compression. We're going to get the same equation, right? It's just the negative sign is going to be different for each one, right? Because in gas expansion, right, for example, let's say we've got some system. Right? Whatever it is, could be a solid that we ignite, creates lots of gas like a bomb, or like a piston in your car engine, right? You got the piston, right? You get the fuel in the air mixture, get the spark plug, piston moves, right on, boop. And then the exhaust gases come out, are expelled, piston comes back up, spark plug, Combustion pushes it down, and the piston goes up and down and up and down due to the expansion and contraction of a gas. So you get a bunch of pistons moving up and down like this, attached to a crankshaft. Yeah, you ever have a thing where you grab it, and you go, and it rotates around? So that piston motion up and down turns a crankshaft, which makes your wheels go. I like cars, but I'm not a mechanic, so that's about the extent of it. But it's pretty cool stuff, right? So you can learn the combustion, that all the chemistry and physics of a combustion engine, right, based on the combustion of fossil fuels, is pretty cool. All right, so let's say we've got some system and there's a gas expansion. Let's say we have on the top of it a movable piston, right? It can move up and down. And the pressure of it has an external pressure pushing against it. Commonly, that's the atmosphere, right? Commonly. So most of the time, the external pressure will be the atmospheric pressure. But let's say we're starting at state 1 here, and the gas expands and pushes against the atmosphere. You got the external pressure pushing against it, and it goes, oh, poof, and it goes up like this. And so you get this change in volume, right? The gas volume increases as it pushes against the external pressure. Oh, that means the system's doing work on the surroundings, which means the energy of the system's going down, so the work must be negative for gas expansion, pushing against the surroundings. Right? In this case, we'll just call it an atmosphere. So we start here, we end here in state 2. And so the distance that piston moves, right, or the height, you can think about it, times the area of the piston would be the volume change, right? The distance or height times the area. That's the volume. And that will be a positive. You're expanding the gas, so it's a positive. So when there's a positive gas expansion, work will be negative. Oh, you see how there's going to be this negative sign in our ultimate equation here because they're kind of opposites? Now let's look at the same thing with gas compression. So let's say the external, the surroundings, in this case we'll call it the atmosphere, so P external is the atmosphere, pushes against the piston, right? So you've got this system this big and then it pushes it down to here. That's your volume change. So it started here, got pushed down to here, boom! So the volume's decreasing. So you got a negative volume change, which is the distance pushed or the length or height pushed times the area of the piston. So we could calculate that pretty easily, something you could do in lab. But since the work is done by the surroundings on the system, the energy of the system, the internal energy of the system's increasing, so work must be positive. So when the volume change is negative, work is positive. When the volume change is positive, work is negative. Oh, I told you it's about the negative side in thermodynamics. So can you see an equation coming here? So we know the area times the distance that piston moves due to gas expansion or contraction is equal to the change in the volume. That change in the volume is key, right? Now remember, we introduced in physics, work is force times distance. Oh, so what's the force? Kind of, sort of. Oh, that external pressure that it's pushing against or is pushing on it has a huge factor in it. Let's see if we can put these two together. Yay! So let's take that physics equation, work is force times distance, and let's take, if you remember back with gases, the definition of pressure. Wasn't that force over unit area? Do you see how these two equations have something in common? Let's do it! I love deriving equations. Let's do it! Did you jump ahead of me and derive the equation for work yourself? Oh, 9 billion extra credit. You never have to take a class again the rest of your life. All right, I'm just kidding. So let's take a look here. So we know a couple things from physics that we derive, right? We know work is force times distance. Oh, push the concrete blocks as far as I can. And then we knew from our gas laws chapter that pressure is force over unit area. Did these two equations have something in common? Oh, force! So let's rearrange this and solve for force and do an algebraic substitution into the work equation. And then let's relate it back to our piston moving up and down. Hopefully you can see the connection as I go. So let's rearrange this. Ready? So let's isolate force. So force will be equal to the pressure times the area, just times both sides by the area, right? Now, can we insert that into there? We can. So let's rewrite this. Let's bring this down. Work is force times distance. But what's force? Pressure times area. Hey, hey. It's time to play. I love algebra. We're going to do this so much more in second semester general chemistry. Lots and lots of algebraic derivation to get these really cool equations in a nerdy sort of way. So instead of writing force, I can write pressure times area, right? Because that's force times distance. Well, what was area times distance? Remember, you take the area of the piston, whoa, that's supposed to be a circle. Take the area of the piston, boop, times the distance that it moves. That was the volume change in the last board, right? That's delta V. Area times distance is the volume that piston moves, right? Right? In that case, if we had that. So we can rewrite this. Oops, I spelled and wrong. It is morning time. So work is equal to the pressure times the change in volume, right? From gas expansion or compression, or contraction, I guess you can think of it that way. Now, we have to add, remember that negative sign issue. If delta V is positive, so let's do this in blue. For a positive delta V, that's an expansion, right? The volume of the system's increasing. It's pushing against the external surroundings. And remember, work is done by the systems on the surrounding. Work must be negative, right on? Because the system's losing energy, expanding against the surroundings. If we have a negative delta V, which is compression, and this would be expansion, that's why I did the piston stuff first, so you understood expansion, contraction. So if it's compression, the volume's decreasing in the system because the surroundings is pushing on the system, doing work on the system, work is positive. So what we just did is combine the two videos. We took some physics, did an algebraic substitution, got the area times the distance, which is delta V, so we got an equation. Now let's look at this equation and see if this makes sense. If delta V is positive and the system's expanding against the surroundings, its energy goes down. So W must be negative, but pressure's, you can't have a negative pressure, so pressure's always positive. And we're assuming constant in this case, right? And this will be the external pressure. Right, that external pressure, which is commonly atmospheric pressure, pushing that either the system's pushing against or is pushing on the system, right? If delta V is positive, work must be negative. But if pressure is always positive and delta V is positive, that would make this positive. Do you see the problem here? And if delta V is negative and that's positive, this would make work negative, but it's supposed to be positive. Oh no, one-handed slap. That's the sound of one hand clapping, right? We need to put a negative sign there. Do you see that? In order to make, because we're taking our frame of reference as the system, we must have the negative sign there. So if delta V is positive and the system's expanding and doing work on the surroundings, its energy goes down, so work must be negative. Since that's positive, you have to have a negative sign to make work negative. And if it's being compressed because work is being done by the surroundings on the system and the energy of the system goes up, work must be positive. But if that's positive and that's negative, we must have a negative sign there to cancel the negative on the delta V to get a positive W. That's your equation for, I just got hungry. You're just kind of talking, all of a sudden just go, I want pizza, right? So I will provide you this on exams. But again, most, I'd say 9 out of 10 easy of our problems dealing with this work is, we're not going to have expansion or compression of a gas, so work goes to 0, so we can just focus on the heat. Yay! But sometimes we have to deal with both of them. So let's take a look at some units here. Gonna get weird, so we're gonna have to define some units here. You ready for some wonky units? Ha ha ha. All right, so work, obviously work is negative P delta V for gas compression and expansion. But the units of work that almost everybody uses today is the joule, right? Calories back in the past. You might get some, I think there's like ergs and British thermal units and some weird ones, right? But we're going to focus on the joules, right? Which joules, what is that? A kilogram, meter squared per second squared, or something like that. But when we do this equation, we're not going to get joules, my friends, depending what your units are. So if your pressure is in atmospheres, which is what most people use, right? I saw torr a lot, or millimeters mercury when I was working on my PhD. But if your pressure is in atmospheres and your volume changes in liters, you're going to get atmospheres times liters as your work units. What? So we need a relation to convert that to joules. So 1 atmosphere liter is 101.325 joules, and that's exact. So that allows you to convert that to something we can use that's not so bulky as atmosphere. But pressure times volume units they're work units, right? You can see it from the equation. The International Union of Pure and Applied Chemistry is really pushing us to use bar instead of atmospheres. Okay, you're not going to see it very often, but somebody might. So you'll end up, if pressure's in bar and delta V's in liters, you get bar liters. So 1 bar times liter is exactly 100 joules. That's a big reason the International Union of Pure and Applied Chemistry is pushing for bars, because they like 100 versus 101.325. And that's exact as well. But if you really want to get into SI units, they like the pressure in pascals and the volume in meters cubed, right? Cubed length units. So if I had my pressure in pascals, which we're never going to do, and our volume in meters cubed, why would you ever do that in a lab? But theoretically, it's kind of cool. You'd get pascals times meters cubed. Now, isn't this nice? 1 pascal times meters cubed is a joule. I went through, just to confirm that, I went through and derived it. I did a bunch of work in my thing, and I went through and converted this to that and this to that, and I was like, yeah, that's kind of cool. Unfortunately, nobody on the planet I've ever heard of uses pascals times meters cubed. Oh, so what I want to do is take a look at this in a different light, using the ideal gas equation, assuming we have like constant pressure, constant temperature for a sample of gas that's expanding or being compressed from the surroundings. Maybe we can't measure the volume changes, but we could look at the moles of gas changing, right? If we're increasing, like a bomb blows up and increases, then maybe you're starting with a solid and it blows up and creates gas, which expands. That's essentially how a bomb is working. Or like in a gun, you got the barrel of the gun, you got the gunpowder, ignites it, creates a gas. That pressure increase pushes the bullet out. Think of that bullet like a piston, but it just ejects out the end at a high velocity, wreaks a lot of havoc. Or if you got a bomb with shrapnel in there, boom, the expanding gas, boom, throws that shrapnel out. It's very dangerous. Let's take a look at how we can look at this in terms of the gas expansion and contraction. We have a busy board here, but let's play around with one special extension of the work equation. P equals work equals negative P delta V. So we know, we'll just talk about expansion. We could do, compression, just reverse the process, right? So we know the volume of the gas is increasing. All right, so there's a couple of ways we could do that. Let's say it's due to a change in the number of moles of gas, right? You can look back at the gas laws. What was that, Avogadro's law? You increase the at constant pressure and temperature, if you increase the particles of gas, the volume has to increase, right? So that would be an increase in the moles of gas causing the increase in the volume. If that happens, for example, there's a lot of equations, but let's take, we're all familiar with TNT. Okay, trinitrotoluene, which looks like this, right? You've got toluene, which is a benzene ring with a CH3 group there, and you've got 3 nitro groups on it. Trinitrotoluene, hey, hey, hey. A little booma booma here. So if we take 2 of those, right, this is solid, and the boom happens, bring down the boom, you get 3 moles of nitrogen gas, 5 moles of hydrogen gas, 12 moles of carbon monoxide gas, and 2 moles of solid carbon. Kind of get a soup there. Can you tell there's a massive increase in the number of gases? That's why you get the expansion of those gases. Fascinating chemistry. Well, in that process, our reactants have no moles of gas. There's none. It's all solid, right? But our products have 3 plus 5, which is 8 plus 12, which is 20 moles of gas. So we're going from 0 moles of gas to 20. Boom! Major volume increase, right? And we're looking at this here. If we keep pressure constant and temperature constant, right? So the change in moles of gas is positive 20. So if we hold the temperature constant and the pressure constant, right, we can look at P equals work. Let's write this down. Is negative P delta V. We derived that before. But we could look at that delta V in terms of gas expansion. Okay? Let's do this on the next board, actually. I'm going to need some room. So we're going to take this work, is negative P delta V, and we're going to rewrite that in terms of delta N. I'm just out of room on this board, but you see where delta N, you just take the moles of all gas phase products minus the moles of all reactant phase products, and that will be either positive in this case or negative, right? If you have less moles in the products and more in the reactants, you're going to get a negative number, and if delta N is negative, the volume is compressing in that case, right? So you're losing moles of gas, so the atmosphere is going to push against your system. So let's do another board here and show you this new equation. All right, this will clean it up a little bit. So we know work is negative P delta V. P is external, or usually atmospheric pressure. But from the ideal gas equation, assuming ideal gas behavior, PV equals nRT, right? So if we have constant pressure, right? Think of atmospheric pressure pushing is constant, and keep it at constant temperature, so this can't vary. Not only the volume and only the moles of the gas can vary. So P times delta V, a volume change due to a gas expansion or contraction, delta N gas, R is a constant, T is a constant, P is a constant, right? Well, there's P delta V. Is it negative P delta V work? So if I put a negative sign here and a negative sign here, then negative P delta V is work, but negative delta N gas, RT, is also work. So we can look at it in terms of volume expansion and contraction, however we do that, or the moles of the gas is increasing or decreasing. So if the moles of gas is increasing, like in our TNT example, right, delta N gas is positive. R is always positive, right? If T is constant, you can't, and it's got to be in Kelvin, you can't have a negative Kelvin, so positive, 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 but we know the gas is expanding, so it's doing work on the surroundings, right? So work has to be negative, thus the negative sign. So that would, if it's a positive delta N gas, then work will be negative. Makes sense, it's pushing against the surroundings. The other way around, if you're losing moles of gas, right? In that case, you can think of a delta V going down, but if delta N gas is negative, that means the surroundings are doing work on the system, the energy must go up. Work must be positive. If R is positive and T is always positive and delta N gas is negative, you need the negative sign there so the negatives cancel and you get a positive work. Negative signs everywhere. Yay! So that's pretty good. I mean, that's, well, let's do one calculation, fairly straightforward with the P delta V, and we'll be done. We're not going to do a lot of work calculations, but just to show you how the units work out. All right, here's just kind of a simple kind of question. I threw a bunch of weird units, so we have to do unit conversions. Yay, unit conversions. So let's say we got a system, right? Some system with a gas in it. Constant temperature, pressure, has a volume of 345 milliliters. We exert upon it a pressure of 764.3 torr, and it compresses the system from 345 milliliters down to 187 milliliters. What is the work done, obviously, by the surroundings on the system in joules? Now, if the work is done by the surroundings on the system, the energy of the system goes up. We should get a positive work for this. Let's hope we don't end up with a negative sign, please. Well, let's think about it. First, let's calculate, well, we need pressure. We got pressure, right? We got the external pressure. We need delta V. So let's calculate delta V. So delta V is V final minus V initial. So what's our final volume? It's 187 milliliters. What's our initial volume? 345. So that's going to be negative, obviously, right? So let's take 187 minus 340. Whoops, I screwed that up already. Negative 158. Do you get a negative 158? You have to leave that negative sign on. That means the gas was compressed, right? Now we can plug this into our work equation. So we know work is negative P delta V, right? We don't have to worry about the moles of gas. There's no information on the moles of gas here. So what's our pressure? 764.3 torr. That's not going to help, is it? We're going to need that in atmospheres, aren't we? And let's multiply that by the delta V. Negative 158 milliliters. So that gives us torrs times milliliters. That's not going to work. But we do know there's 760 torr in an atmosphere. So we can convert that to atmospheres. We know there's 1,000 milliliters in a liter. So we could get that into atmospheres liters. And remember, what was it? 101.325 joules per liter atmosphere? Unless we did this in bar, right? Then there's 100 joules per bar liter. Unless you want to go to pascals and meters cubed, then it's a one. No, we don't want to do that. So let's convert torr to atmospheres, assuming that's an exact conversion. Let's convert milliliters to liters, and then the torrs cancel. Milliliters cancel. It gives us atmospheres times liters, right? 101.325 joules per atmosphere liter. I don't have a lot of room. so this will be joules, and it's 101. Sorry, I had to squish that in there, but there's 101.325 joules per atmosphere liter. So if we punch this out, see the negative signs are going to cancel. It's going to give us a positive work. We need a positive work because the energy of the system's increasing, right? So let's take 764.3 times 158, and the negatives cancel. Let's divide that by 760. Let's divide that by 1,000. Let's multiply that times 101.325 joules per liter atmosphere. So I get 16.09999, right? So we've got 4, 3, exact. Oh, that's exact, right? But it doesn't really matter. So we're limited to 3 significant figures. So 16.0. Let's pop that vertical dashed line, and then I get 2 nines after that. Joules. I'll provide you that conversion factor and that conversion factor. I don't give you the metric ones. I can take you over. So that's going to round up to 16.1 joules. That is the amount of work done by the surroundings on system, right? That's by the surroundings. That external pressure, the atmospheric pressure, is pressing against the system and compressing the gas. Therefore, the energy of the system increases by a rounded value, 16.1 joules. There you go. That's work for you. Lots of physics, but let's get back into heat. That's our comfort zone. It's a comfort zone for science, for chemists. We like heat.